I'm going to talk about sequential containers, right? Specifically in C++, we're going to deal with arrays and vectors in this course. So, first thing we're going to talk about is about memory and how it's allocated. Now, you might have been accustomed to a statement like int x. You would have heard in class before that this is a declaration. What this line actually does is it allocates memory under the hood. So it's like this little box here on the right-hand side, a little space in memory that is allocated to be able to hold an integer, okay? But because we haven't put anything in it, whatever's there in memory will, well, be in X. In this case, it's just some random garbage value, okay? We can, however, use a line like x equal 10, which assigns 10 to the variable x. And that just puts 10 into the little container that holds integers called x under the hood. Similarly, we could both declare and define y at the same time, another variable. Here we're putting 34 into y. That's the same equivalent of making another box under the hood and putting 34 in it. Similarly, you could overwrite the contents of x by putting 7 in it. Okay, whatever was there just disappears and this new value goes. We can also take whatever's in y and put it into x. Now, I want you to realize that what the equal sign actually does is it assigns it, which means it takes a copy of what's in y and puts it in x. Therefore, it doesn't hurt y in any way whatsoever. Whatever was in y remains the same. And of course, you would know you could do arithmetic on it as well. We could say x plus 5 and then take what the result of that addition and put that result into y, right? Again, that doesn't affect x in any way, okay? And that's memory allocation in a nutshell. Well, what does this have to do with arrays? Arrays are just like the memory locations x and y we saw before. However, arrays mean that we can form a collection, a group of things. So here what we're doing is we're creating an integer array of 3 integers, okay? So under the hood, what happens is we can allocate 3 locations that could hold integers. And just like the declaration from before, there's just garbage in the memory right now. We've allocated the space, but we've never said what to put in it, okay? Although we could put something in it alongside the declaration. This is called defining the array in one move, where you put 56 in the first location, 32 in the second location, and 43 in the third location. Now I want you to recognize that even though there are 3 locations, each location goes by a specific number. And that numbering starts from 0 up to 1 less than the total size. So I can now do something like this. I can say at array location 1, I want to put the value of 10, right? This is the same way I would have put a value into the variable x. It's just the whole name of it is actually ARR with some square brackets and a 1 on the inside. If I want to put something in a specific location, I have to put it in the square brackets. That's known as the indexing operator, right? Similarly, I could create a variable called x and take what's in array location 0 and put it in x. Okay, so I want you to recognize something here, that I'm using it in the exact same way I was using the variables x and y from before. And that's okay, because even though ARR is an array, each array location holds an integer, and therefore I can treat each location alone as though it was just an integer x or integer y, right? As I did before. That's all you have to think about. What is the type I'm dealing with, and the ARR with the square brackets after it will give you the integer type, right? A box that can hold an integer. So how would we output the elements of an array? Let's think about that right now. One strategy is you would see out every single line. That will require me to write, well, see out each one. But if I had an array that had 100 elements in it per se, then that would take quite a while and it'd be very annoying to write. So how do we actually deal with something like that? So first, you probably want to recall that with a for loop, we can actually run I from 0 to 99 if I wanted to, very easily. That's what a for loop can do. And all we'd have to do is now just substitute in the array values in there and use I in the square brackets. Because each time the for loop runs, it would do array 0, then it would do array 1, array 2, all the way through all 100 items in the array, if the array was 100 items large. Okay, so I want you to notice and recognize that for loops can be used to walk or traverse arrays. That's what this structure is called. It's called walking or traversing arrays. And this is a very important type structure because we do it over and over again, because sometimes we have to affect all the elements in an array or in a collection in general. So walking and traversing arrays is something you would see recurring over and over. Okay. Now let's think of some common mistakes you might make. Now let's imagine we have an array that had 3 items in it. Now let's take a look at where this for loop is going to run. This for loop is going to go from I equals 0 to I is 3. It would do 0, 1, 2, and 3. So therefore, we will output 4 locations. Array location 0, array location 1, location 2, and location 3. But the array only has 3 locations in total, 0, 1, and 2. There is nothing stored at location 3. What would happen if I try to access or read that location? Well, when I ran something like this, you'll notice on my output window, I got the 3 values at first, which is the 50, 34, and the 66. And then I got some kind of garbage location, some kind of garbage memory read. So if you read something beyond the end of an array, you'll just get some kind of garbage. Sometimes your compiler might even block you from doing this, saying you're reading to unknown space, or sometimes it will silently just try its best. Because I'm reading beyond the location of this array, there was nothing stored there, and therefore it was just garbage in the memory, and just gave me back that garbage. Okay, but that's reading from it. What happens if you try to write it? So let's say we wanted to put the number 9 to every single location in the array, right? Again, I'm doing the same thing, and I'm going to try to write the number 9 to the 4th location. That's one beyond the end of the array. Well, what happened when I ran it was I got this big debug error coming up at me. This is an example of what you call a runtime error. Okay, runtime errors means that while the code is running, something bad happens. And in this case, it's telling you, well, you tried to access a memory location that it never allocated. It's trying to stop you from doing that. That's a bad idea. Okay. Another common mistake that you might make is that you might try to output the entire array as a whole, right? Instead of doing it element by element. So what would happen if you just tried to output ARR instead of trying to output each element one at a time? Well, this is what happened when I ran it on my computer. You'll notice that there's this big long address here. This is actually the address where the array is stored on my computer. Okay, we'll go more into this in a much later class, but it doesn't do what you'd expect. It wouldn't output all of the elements of the array, it just outputs the address. Okay, so now let's come to some actual problems with arrays. One of the biggest challenges with arrays is that you can't change the size once you allocate it. So if I made an array that has 3 items in it, I can't go and change that while the code is running. I just have 3 locations. That's why this is called a statically allocated contiguous memory. Contiguous memory refers to things are stored one after the other. Statically allocated means that it's allocated just once at the time you write your program, and that's it. There are such things as dynamically allocated arrays, but I won't go into that. So the problem with not being able to change the size and the fact that the size is determined when you're writing your code is that a lot of the time you don't know how someone's going to use your array uh, at runtime. So let's say the idea was that someone had to enter indeterminate number of values at the command prompt, at the user prompt. Well, it could be that you've allocated too much space and therefore you have a lot of wasted memory, or you've allocated too little space and you'll end up trying to write beyond the end of the array location. So arrays are a little limiting from that perspective. A lot of real world problems can't really be worked with static arrays. So you have to turn to a more dynamic structure. So it's either you learn to write dynamic arrays yourself, or you actually use something that could dynamically do it for you. And vectors can do that. So that's where vectors come in, right? So if I had to make a vector, I would make it in the same way as the array. I could use the exact same line or something very similar. This line here says that I'm creating V, which is a vector, and that vector is going to hold integers, right? And again, we're just allocating three things to it. Now, a difference that you would notice that I need to do a hash include vector for the C++ library, as well as the namespace, because vectors in the standard namespace. Right? But I could do everything in the exact same way. I could put 10 into location 1. I could read from location 0 and put it into a variable called x. And I could do some arithmetic on it in the exact same way as before. So here it is just for you to see the differences side by side. I did the exact same code, and really and truly the difference is that I have to include a library with vectors, and I have to use the namespace, of course, using the standard vector, and how you declare it is a little different. But other than that, everything remains the same. So that might bring you to ask, well, what actually is the difference here? Vectors actually come bundled with a bunch of other stuff that make it a lot easier to use, right? So first off is to deal with that problem of not being able to resize on the fly. And that brings us to our first difference. We could use something called pushback. So let's look at some basic code here. We've included vector and the namespace, and we have declared it. Now notice I have just declared it, which means that there's nothing inside the vector. So unlike in the array where you had to create a size, in this case, there was no size here created alongside the vector. So there's actually nothing inside this vector. There is no memory whatsoever allocated, right? It's just a blank space. However, if I do pushback and I put pushback 5, what that does is it actually creates a memory location under the hood that can hold an integer and puts 5 in it. And this is the 0 at location that's actually created, index 0. If I do pushback again and I put 7, it creates another memory location and puts 7 in it. And this is at location 1 now. And I can keep doing this pushback process and keep putting more and more things inside it, right? So pushback allows me to keep allocating space as I need, right? So I can allocate as many as I need just by just keep writing pushback and putting whatever number I want. So it does not matter how many things someone were to give me from the input, or if things were to change on the fly, I could allocate the space as I need. And that's one big difference between vectors and arrays. Vectors, I can do this thing and actually put things as I need, right? So pushback is used for dynamic allocation. So if we didn't know how many numbers someone was going to give us at the command prompt, pushback is a thing we could use. So that brings us to a brand new problem. With arrays, if we set the array to a certain size, well, we know it can't have more than those number of things in it. So how do we actually know how many things someone has entered? That actually brings us to our second big difference. That has to do with the size member function. So if I had a vector v and I push back 5 in it, and I did int size 1 is v dot size, right? That means I only had one thing in it at the time that size 1 ran. That line ran. I would only have number 5 in it. So therefore, size 1 will contain one item. Or if I were to push back 7, 11, and 13, then at that point, size is now 4, right? So if I ran v.size and put that inside of an integer variable, SC2 or size 2 is actually 4, okay? Because that's the size of the vector. So if you want to find out how many things are inside of a vector, you just have to put dot size at the end as a specific member function that will tell you the size or the number of items in the vector at any point in time, right? Similarly, if I wished to output all the elements from a vector, I could walk or traverse the vector in the same way I could walk or traverse the array, right? I could go from I equals 0 to v.size, incrementing I as I go along, and output all of the elements. And that will work fine. There is one note I would add here too. The problem is that int is not actually a good type to use here, okay? Int as a type can hold both positive and negative integers. But the size of vectors and the size of arrays are always positive numbers. It can either be 0 or more. Okay, so that means that int is not the best type to use in this case. Some people might say, well, why not unsigned int? Well, it's actually a built-in type called vector int size type, right? This is the actual type that is built specifically for vectors. If somebody were to change under the hood as to how many things a vector could hold at maximum, this would always work and not break your code. However, I do recognize that it's a little long, and some people might not remember that very long statement. So if you can't remember, use the word auto, which lets the compiler choose the type for you. Right? So moving along now, what about removing elements now? Okay, well, if you have to remove an element in a vector, the thing you have to think about is which element do you want to remove, right? And we need a way to indicate which element we're talking about, which element we're actually going to remove. So first off, let's think about how we could point to which thing we're talking about. Let's pretend we had a vector with 4 things in it, right? There are the 4 things. I'm going to introduce something called an iterator. Iterators point to a specific place in a container. It's purpose-built for any container in the standard template library. Okay, so in this example, if I were talking about vector begin, or v dot begin will always be talking about the first element in the vector, right? V begin plus 1 would be the second, plus 2 would be the third, and plus 3 would be the fourth. Okay, so if you want to talk about 11, 11 is at v begin plus 2. Hope that makes sense, right? And on the other hand, is a little special in that while begin points to the first element, end actually points to one beyond the last element, right? Which means that the last element is actually at vn minus 1, and second to last at vn minus 2, etc., etc. Okay, and this is of course assuming we only had 4 items in our vector. Okay, so what if I wanted to remove the second element, right? So there is a function for that. It's called erase, and that function erase takes an iterator. So in this case, v.size is 4. So if I wanted to remove the second element, I would have to call erase and give it an iterator to which one I want. So what iterator would that be? So if I were using begin, it would be begin plus 1 because the second element. If I was using end, it would be end minus 3. Okay, so I guess the easier one to use for most people would be the begin. So v raise would be v begin plus 1. And after you've run that, The first thing you should note is that v size will now go to 3 because while there were 4 elements, now there are now 3. And you will notice that the indexes have now changed, right? The indexes from before, number 7 has gone, so 11, whereas it was at location 2, has now gone to location 1, right? Indexes are always in order. So when you erase something, the order still has to remain. Okay? No missed off or missing or blank spots or anything like that, right? So on your own, I want you to think about it. How can you erase the last element of a vector? Hopefully that should be pretty straightforward, right? And what about if you're actually inserting in the middle of a vector? Well, it'll be the same exact concept, right? We would use insert, right? And we would insert at a specific iterator position and a value, right? So what if you try to put something in at the start of a vector, right? I'll leave it to you to give it a whirl and see what happens, okay? So beyond that, I think you now know a lot of the basic functionality of a vector. There's pushback, size, erase, and insert. Those are the most basic ones. And understanding iterators also allows you to use some of those functionality. And the iterators you could use are begin and end. We will get into those kind of topics a little bit in more detail later on. But for now, the thing you have to kind of focus on is how you use the vector. So if you can, try to find the total sum of all the numbers within a vector. So take a vector, put some numbers in it, and see if you could find the sum of it. See if you could find the smallest value within the vector, or if you could find the average value of all the numbers within the vector. All of these should be pretty straightforward and a good start before you come to do your problem sets in the lab. Okay, that brings us to an end of this talk, and I will now stop the recording.